this is my mandatory slide saying I might be lying. Don't make any decisions based on anything I say. This is the only way they'll let us speak in public. So, I'm Attila. I work with Oracle in Java Lang Tools group, and my day job is pretty much building this new, improved Rhinoceros named Nashorn, which is a so Nashorn is basically a JavaScript runtime. Well, technically an ECMA script runtime, but everybody calls it JavaScript. It's open source. All of its development happens in the OpenJDK, and it is part of Java since version 8. There is several ways you can use it. It doesn't really have its own API. It's all meant to just run through the JavaX script API, which is pretty much ancient history. It exists in Java since version 6. There is some specific functionality that can be used through JDK Nashorn API scripting package, and you can use it from command line as well in your Java home directory bin. There is a JJS binary, which is quite silly because Java actually comes with a bunch of utilities that have J as the prefix, right? So there's a JPS, which is the Java-specific process listing, and the JJS is the Java launcher for JavaScript. Nashorn has no interpreter. It always compiles to Java bytecode on the fly, which let's show it in its startup times, but we'll get to that. So what I will not be talking about here is why would you use JavaScript on the JVM in the first place. There are a bunch of valid reasons. You might want to integrate a library on an algorithm that's written in JavaScript and you don't want to recode it. You might be building a large system where you're actually deploying on the JVM, but you might want to hire talent that is able to program in JavaScript, and you want to have an application customizability layer on top of your stuff that might be programmed in JavaScript. There's a bunch of reasons why you would like to do it. I also will not be talking about how to use Java-specific features from JavaScript. I gave a few talks about that, and there is all kinds of platform integrations, how you can pass JavaScript functions wherever lambdas are expected, how you can obviously create Java pojos, you can subclass Java classes in JavaScript, and so on and so on. That's all possible, but I will not be talking about here. What I will talk about here is mostly performance. My background with Nashorn is, these days I'm mostly working on the compiler backend, but I actually did work on almost all aspects of the runtime. So Java linking, the parser, the other aspects of the runtime. And I will talk to you about what is it that we do to make sure that Nashorn actually runs fast. I will try to give you a glimpse of what actually happens under the hood. And I will also talk about it that should you choose to integrate Nashorn in your system, what is it that you need to do in order to have it run fast? So in the first place, what did we do to make Nashorn run fast? Well, we did a lot of things to make it smart under the hood. Compared to the initial Java 8 release, the stuff that we have in Java 8040 is already pretty advanced. We did all of this in a span of about a year. We have lazy compilation of functions that is specialized on the types of the parameters. We actually have static type inference for local variables in JavaScript. We have a thing that we call optimistic typing, which is a fairly big deal. This is basically type speculations. All the types we cannot prove, we will make some assumptions on them, and we can actually de-optimize the code if the assumptions prove wrong and generate a new version of the code, and let's run with that. So if we did all these smarts, what's left then, right? Well, what's left? What's left on our side is still there is a billion of optimizations that can be made. I didn't even touch some fairly typical compilers type stuff like hoisting loop invariants, constant propagation, and so on that I hope to get to one day. But there is also something that you, as a user, if you want to integrate it in your Java-based system, you will need to pay attention to. You will want to avoid doing really stupid things because JavaScript is such a flexible language that you can easily write programs that defeat the compiler. And it also matters how do you integrate it into your Java-based system. So I'll show you how do we do our smarts. So for instance, parameter type specialized compilation means that if you have a very simple function here that just takes an argument and squares it, if you actually invoke this guy twice and pass it an int once and pass it a double the other time, Nashorn will actually generate two code versions. One that operates on ints and another that operates on doubles. You can see them there on the right side. I have this handy clicker, but the angle is such that I don't think I can actually hit anything reliably. Nope. So, and you can actually see this in action. I have the code right here. Yeah, font seems big enough. So if we run this code, then fairly non-charismatically it prints whatever it does. But if we ask it to spill its guts for us, it will actually show us a bunch of code that it generated. And you can see that at first it will generate a version of the function that takes an int and returns an int. It actually optimistically presumes that multiplying the two ints actually won't overflow, and it fortunately doesn't. And here you actually see the output, and you can see that only after that it generates the second version that takes a double and returns a double, which has a very straightforward implementation. So this is all live. And after this was done and some additional stuff that's going on, you will actually see the second line of the output. What's nifty here is that code, a particular specialization is only generated first time it is invoked, but of course then it's retained and will be reused the next time. So what does the static type inference do? One thing that is used to measure implementations of JavaScript runtimes against each other, each JavaScript runtime usually comes with the benchmarks that sort of try to put that particular runtime in a positive light. Well, Nashorn doesn't have any of those. We just don't really, I don't know, either don't have the capacity or don't care. We just adopted Google's V8 Octane benchmarks. And one of those is a cryptographic benchmark, which is a heavy number cruncher. This function, you don't have to understand it. This is just the hottest inner function in the cryptographic algorithm. So our static type inference, if you just let Nashorn static type analyzer, it will do something similar to that. So the things in the red brackets are the types. These double O's object, I is int. And what happens here is that these are not terribly nice. So the bad things that you see is that decrementing an int has to presume that the result will be a double because it might actually overflow the int range. And then also you can see how the variable L further down there actually has to be an object. Why does it have to be an object? Well, unfortunately, because there is also this access to an array in there. I really wish I would be able to use my laser pointer. Doesn't? Okay. So there is an access to an array which is then added to something. And in JavaScript, the plus operator is so unfortunately overloaded that we don't know. Maybe the array will return a string, and then we have to do string concatenation. And in that case, this value might just well be an object, right? And again, the variable for the value for C has to be presumed to be a double because there's a multiplication going on in there, which also can overflow. So we have static type inference, and it helps, but it doesn't help a lot. Now, when you combine this with the other feature that we have, optimistic typing, you actually get these kinds of types. And this looks much nicer. All the trouble spots are gone. And as you can see, the only variables that remain being objects are this array and w_array, which are objects, they are arrays. And everything else will be presumed to be an int and won't overflow and so on. So if we actually generate code for this AM3, it looks pretty much as if it would look like if you just wrote the same algorithm in Java. Let me show you. I actually have this whole crypto benchmark here. As you can see, it's a fairly biggish JavaScript program with a bunch of all kinds of calculations and number crunching. It's great because it's not doing I/O, it's not doing anything like that. There's not really any JavaScript performance story in, hey, we are fast at I/O, because JavaScript doesn't have its own I/O libraries. So if you were doing that, you would just delegate to Java anyway, and then you are as fast as Java. So it's really algorithmic performance that contains the interesting things here. And so if you run this guy, as you can see, it generates a truckload of code. Then if I try to find the implementation for the AM3 function, you can see that it mostly is doing iload, iend, iload, ishift. So if you read Java bytecode, then you can see that all of this are integer instructions. And pretty much if we scroll down and take a peek at the local variable table, we will see that this, aside from the arrays, all of the other variables have the type int. So yeah, yes, question here?
Why do you do invoke dynamic to add to integers? Is it to
all right, so the question is, why do we do invoke dynamic to add to ints? The answer is because it can overflow. This invoke dynamic is linking to a function that does the addition, and if the result overflows, it throws an exception which forces us to recompile the code with wider types. So, and synergistically, this is actually this is a nice word, but it's been so horribly co-opted by marketing, right? So marketing people are always like synergy, and what it actually means is result of an action of two agents or effects that have a combined effect that ends up being more than the sum of its parts. And for us, the type inference and optimistic typing and lazy code generation and type specialization all lead to some really nice results. Like in Nashorn, we have higher order functions that are type specialized by using all of this. So if you have this higher order function named twice that takes another function and an argument and just returns the original function applied twice, and we pass it the increment function, which is just plus plus plus, then if you invoke this with 5, you will get specialized version of the function that takes an int, returns an int. And if you invoke it with double, you will get one that takes a double and returns a double, although it actually does it in several steps. Because if you do it with double, which is interesting here, at first, if you generate a version that takes a double x, but it still hopes optimistically that it might return an int. And then when it actually gets invoked with the inc function that takes a double and returns a double, it will notice that, oh well, my first application returned a double, but maybe if I apply it again, maybe it will return an int. And then next time it also doesn't return an int, so we actually de-optimized, evolved the function all the way down, where we say that the twice, if given something that takes a double, will return a double. Now, of course, if you later on pass it another function that might take a double but still returns an int, it will now remain widened to int. So we don't really have full dependent types. So that's and we probably never will. All right. And of course, the int version still remains there. So if you again invoke it with an int, then the int version gets invoked. So we have this nice nice type story. The question is also, so when we did this thing with, sorry, got confused. There's a question there. So.
Hi, I was wondering what you just mentioned about higher order functions being specialized. Yeah. Sort of implies that specialization is viral across the call path of whatever code base you're sort of compiling at the time. So are there any sort of limitations to avoid metaspace poisoning with, just really, really deeply nested specializations or other limitations that?
Okay.
we should be aware of, I guess?
Well, in a worst case, you could have a combinatorial explosion of code, but obviously we have the Nashorn's type tower has 4 types: int, long, double, and object. And every function is compiled on its own, right? So you can have at most 4 to the power of number of parameters versions of a single function. Now, when it calls another function, that function will be separately compiled with whatever types it was invoked at the call site. So basically, there is no such thing as, well, yeah, I mean, obviously, as you are tracing your way through your call path, you will be generating new functions. But again, yeah, you could have a theoretical worst case code explosion if you have a function with 8 parameters and for some reason you manage to generate all the combinations, but you have to have a statical call site that will actually generate that signature first. So that also limits the potential for damage, so to speak.
Okay, so you could do something really, really bad like craft code that does, you know, up to 4 to the power of whatever nesting you have, but you need to do it statically.
Yeah.
It'd be insane.
Yeah, but you will need to generate that code so that you will need to have to force it to statically contain call sites that produce those type signatures. In most practical applications, I don't believe this happens. We also unload code that's not referenced, so.
Okay, thank you.
Welcome. So, also, this is a good question. How do we de-optimize running code? So, because to de-optimize running code, we must be able to recompile it on the fly and then replace running code on top of the stack. And we do actually have a pure bytecode solution for this. We're quite proud of it because it runs on any JVM. There's no Oracle hotspot trickery involved. So you can take Nashorn, which is OpenJDK part, and you can run it on IBM's VM or anything else. It will just work. So we actually do this by driving it with the exceptions. Exceptions are thrown to the caller, at which point we derail into the compiler, generate a new version of the function with wider types, and we also generate a one-time continuation from that point where we interrupted execution with the narrower types, and then we jump back into that. So it's technically fairly involved, but you know, it took us a few months, but we got it right eventually. So the next part of the talk is about writing a small web application. I show my age because I will use the Servlet API. There's a bunch of very nice new frameworks, Vertex and Node.js and whatnot, but this is Java, and we use the Servlet API. I could have just used command line as a matter of fact, but Servlet API is nice because then I can benchmark this thing with Apache Bench, which is, I guess, a plus. So I have this very little, I love Jetty. This is all you need to set up a web application with Jetty. You create a servlet content, you add a servlet, and bam, you start it, and the thing just runs. And I wrote a little servlet that's running the crypto, which is just setting up the request and the response, and the do-get or post will just do some rudimentary HTML, and it delegates all of its guts to this evaluate function, which is actually abstract, and then returns a response. And I coded up a bunch of various ways to evaluate this crypto library. And if we start this thing, and the demo gods are with us, they are, then I can just go to localhost 8080, and it will eventually start up. So it's just a field. If I submitted it, then what it does, it encrypts it, round trip decrypts it, and then shows you how much time did it take. It's really very simple. It's not a big deal. If you submit it once again, now it becomes much faster, and eventually it will be warming up. So there are several strategies to integrate JavaScript into your Java runtime, and I'll tell you why do we actually have several strategies. Why don't we just have one strategy, right? And the answer is a little bit surprising. So the most naive approach you can integrate dynamic language runtime, not just Nashorn, but any dynamic language runtime into your Java program, is that on each request, you start a full instance of your language engine, and you evaluate a script into it. Now, you can do that, so one implementation of this evaluate method could be that, and this runs on every request, right? You just take your script engine manager, you ask for an engine, evaluate the script into it, and then invoke functions in it. You can definitely do this, but it's not terribly efficient, so I could be running this now in Apache Bench, but considering how we only have 25 minutes more, I'd rather not. It's slow. So how well does it perform? It doesn't perform very well. The 50th percentile is more than 2 seconds. The first request might take more than 7 seconds on my machine. So right, this is not usable. I actually looked into where does the time go, and most of the time is one-time code setup, which is not surprising because Nashorn will be parse and compile to bytecode and give it to the JVM, which starts interpreting it, and then it needs to link, invoke dynamic call sites. So most of the time is actually spent in chain call site, relink internal, and in class loader, install class, and so on. So most of the time is basically spent in code management. So, all right, so using a new engine for every request is obviously not a terribly good idea. So what can we do if you just use a single engine instance? Basically, I now shuffled off the engine into a static. In a servlet world, obviously, this is not what you do, but rather you bind it into your web app or servlet context or whatever it is. But for demo purposes, it's good enough. And then I'll just evaluate the script in this engine every time, but I'm reusing the engine. Now, this also looks shaky, right? Because I'm opening a reader, and it looks like I'm actually reading the code every time. It's not so bad, though, because if we measured this guy with Apache Bench, it actually performs fairly decent. You still have the longest request will still take about 3 seconds because it needs to initialize the Nashorn internals and the engine and the script and everything. But then it gradually becomes faster. But that URL reader is still sort of not terribly nice there. However, Nashorn is actually smart. So if you pass a URL reader, it will notice it actually has a code for, oh, is it an instance of URL reader, this reader that you passed me? It will then cast it, look at the URL, and it actually caches the code. So that's why it's fast. It does open the URL reader, but it doesn't really read it if it already has the code cached. So at least that's smart. Of course, you might ask, why don't we have an API where you just pass a URL? Answer, because javax.script API doesn't have one. Wasn't me. So, however, oh yeah, that's what I told you, basically, that you can regulate the size of the class cache because you probably don't want it to get away too high. By default, it defaults to 50 scripts, but there is a Nashorn command line switch that you can use to specify the size. If you want to avoid this whole deal with URL readers, you can use another feature of the JavaScript API, which is the compilable interface. You can take an engine, you can cast it to compilable, at which time you can actually ask it to give you a compiled script, which is a theoretically optimized representation of your script. And then in that case, so what's different from the previous is that you just compile it, and then after that you will always be evaluating that compiled script. However, there is some things that go around above the second underlined line, which is, as you can see, I'm doing this engine.createBindings thing. That basically creates a new global variable space for evaluating that particular script in this request, which will then be populated with its own instance of built-in JavaScript objects, the global function object, the global object, global string object, and so on. These operations are fast, but it still has to be done. So how well does this thing perform? Better. So as you can see, the reader compared to a compiled script, you will gain an edge. So it goes from 50% from 195 milliseconds ago to 159. So it's, again, a little bit faster. there's also the question, are we evaluating everything? Because there's an eval call on every request, so all the functions that are defined in crypto will be populated into this global scope. Again, this is something that you theoretically have to do because your JavaScript program is evaluated every time. However, this is fairly cheap because all those functions are just first-class objects. So what happens is that you just populate your top-level global scope with already predefined, well, code objects, basically. So that's cheap to construct and runs pretty fast. As you can see, it's like 159 milliseconds to evaluate the whole crypto operation with the setup of new bindings every time. So the reason why there is several different ways that you can separate the evaluation and the compilation, you decide whether to cache, you decide whether to evaluate repeatedly and so on, is because JavaScript and a bunch of dynamic programming languages don't really define separation of compile time and runtime. It's just not in the specification. JavaScript specification basically says, here's some source code, here's how you run it. It doesn't tell you how do you get from the source code to the execution. There's no specified intermediate representation, there's no telling when do you need to parse the full source code even. It's hand-wavy. You can implement it any way you want. And then when you try to integrate a dynamic language runtime into your Java runtime, where you're used to compiling code and packaging it and so on, suddenly you realize that, oh my God, I have more freedom than I really want, right? Because now you have to deal with these aspects of where do you cache the code? Are you sharing global namespaces or not? So you're probably thinking, so what if we just reuse the bindings object? Why if we just reuse the global scope, right? You can do it. Here's another version of this crypto program where, of the servlet, which just evaluates the script once into the engine. The engine has a default global variable namespace. And we extract the encrypt function and the decrypt function into static fields. And when we evaluate, we just invoke them. So how fast is this? The previous one was 150, 60-ish milliseconds. Well, this just got fast. Now we are down to 30 to 50 to 60 milliseconds because we are not redefining. On every execution, we don't have to define all the functions into the scope. We just define them once, and then we are just invoking them. Every request comes in, bam, bam, bam. We are just invoking this thing. I might actually spend a bit of time to show you this. Yeah, this is actually the exact same version. So I named all these classes in the order they come on slides. So this is the number 3, single bindings, which, as you can see, does exactly this thing. It takes the encrypt and decrypt function, extracts them in a static block, and then just evaluates them. Evaluation is just these 3 lines where it just calls the functions. And if we try to benchmark this guy, then it will probably come, hopefully it will come pretty fast. I didn't want to show you a benchmarking with the first one because that was 2 seconds to 7 seconds for one request, so 1,000 requests. Actually, it would be a really great talk, you know. I just put the benchmark and it's running, and I don't know, I entertain you with jokes in the meantime. To be honest, even this is too slow for a presentation. I'll cut it down to 500 next time I'm presenting this. Yeah, so you can see this is pretty much the same ballpark, 36 milliseconds to 82 and so on. I just wanted to show you that I'm not really pulling out these numbers out of thin air. I did actually, honest to goodness, benchmark this on the same laptop at home and populated the numbers on the slides. Well, yeah, but is this thread safe, right? Obviously, I mean, foreshadowing things here, obviously it's not. However, it might be okay to do it. So, and this was all without turning on optimistic typing. Optimistic typing was off for that. So if we turn it on, and to turn it on, we now need to use Nashorn specific API, because now instead of, if we go back here, you see the first line says engine equals new script engine manager, get engine by name Nashorn. And here, I actually am doing something else. I'm doing new Nashorn script engine factory. So I'm taking a specific, I'm asking explicitly for a type of creating a Nashorn specific script engine factory, because again, it has additional API methods that are not present on the generic JavaScript API. Namely, you can do a get script engine and pass command line arguments, which is good if you want to pass other Nashorn command line arguments to your custom engine. So we turn optimism, and this is what we get. Thing actually got even lower. So we are now 2 times to 3 times faster than non-optimistic. So we've gone a long way from the horrible worst case to the reasonable normal case of 160-ish milliseconds down to 12 milliseconds per request for the 50th percentile, and even the 13th percentile is 99th percentile is just 30 milliseconds. So this thing got really fast if you turn on optimistic typing. It is slower to start up though. As you can see, the startup goes from 3 to 4.7 seconds. But this is because we have this thing where we generate a version of code, start running it, bump into a type limitation, have to bail out, recompile. So the warm-up, so there's a startup churn with this. I measured it, and 35 functions are recompiled 67 times total in order for the crypto benchmark to run once. But of course, once it ran, afterwards it's faster. Actually, we'll skip over this. Yeah, so it's mostly like if you are having gears in a car, right? So, sorry, question there? Well, okay, so the question was how much memory does optimistic take versus non-optimistic? Well, it doesn't take more, because once a code variant is invalidated, it is unreferenced, so it will be unloaded. So you have to separate type specialization, where we can have 2 versions of a function with different input parameter types, and we will keep both of them. On the other hand, de-optimization works on a type specialized variant, and you always have the current most de-optimized state. And whenever you de-optimize, the previous de-optimization, the previous state is thrown away. So you will only have the current most de-optimized state. So it doesn't take more memory. Question there as well. Oh my God, we won't finish with this talk unless you're willing to sacrifice your line in the lunch. Yep.
You mentioned that for optimistic typing, optimistic typing, you first assume pretty much that all of the types involved are ints.
Yes.
I was wondering if as sort of a startup time optimization, you couldn't not make any assumptions, but instead on the first run collect the type information and then opportunistically compile for that.
All right. So yeah, we could. That's actually what most JIT runtimes actually do. Collect type profiles, then produce an initial optimized variant based on that, and then work backwards from that. We currently don't do that. It would be a strategy, but we are not doing it. It has a bunch of additional problems where we don't want to, say, pollute globally observable objects with wider types than necessary, so elements in arrays and so on. So if you did this, then every array setter would need to, because then you would run pessimistically and just run with boxed doubles for every number and so on. But if you would be setting this into an object property, then you would need to check on every set operation whether it can actually be represented as an int and then stash it as an int into the object or array and so on. So it has a bunch of additional technical problems, which is not to say that it can be done, it's just that it was a design decision by us to not do it. We do other things to reduce on recompilation. Again, since JavaScript doesn't distinguish runtime and compile time, our compiler, when it comes to running at the optimization, it actually can peek at the current values in the function. It can evaluate side effect-free expressions, traverse object chains, and if it notices that some other value than the one that triggers the optimization is also wider than it presumed, then it will already emit code for that also widened. So that's how we actually cut down on the number of the optimizations significantly by just making sure that whenever the optimization happened, then we just look into all the objects that are available in the runtime lexical scope. And if some of them already say this property already has a double, so if I'm dereferencing that property, I will emit that call site as a double already. We do that though, but you're right.
Okay, thank you again.
Yep. So yeah, the problem is we don't have an interpreter currently. We are sort of thinking about adding an interpreter maybe. And if we had that, we would have fast startup time, and then we would also be able to collect profiles. Actually, we could even do things with the interpreter that we can't do with compiled code, which is, well, I won't go into that. We could do reuse of call sites in the interpreter. We can do this for particular reasons in compiler. That's too technical for this now, but it would be valuable. However, you can also cut down on recompilations if you use Nashorn's typeinfocash. We can do things where the Java runtime can, in system-specific cache directory, so on Mac OS that will be user home per library per application support caches, com Oracle, whatever, it can actually store the discovered information for particular functions. And it's cryptographically safe. The way it's stored is we hash the Nashorn code and we hash the function being stored, so you cannot really have a miss. So what happens is that if you turn on the Nashorn typeinfo system property, then whenever a function is compiled, it will see whether on a previous run of the JVM it did actually already compile this function and to what state did it de-optimize it. So if we do that, we actually cut down on startup time somewhat. So if you look at the non-optimistic, had the startup time of 3 seconds, and optimistic was 4.7. If you use the type cache, you get down to 3.5. So it's still a trade-off. It's still slower than optimistic, but it's a trade-off we'll have to live with for now. And of course, we get back to the, well, yeah, but is it thread safe question? I did integrate a little bit of a check into my servlet where it does see whether the plain text equals whatever it was the round trip of the plain text, and if it doesn't, it will respond with an internal server error and also log that there was a race condition. And if you actually, I have a version of the servlet that is intentionally stateful, so it puts thing into the global scope. And if I run Apache Bench into Windows with those two versions, then I will actually be starting getting non-2xx responses, so I'm actually triggering race conditions. And of course, that's because shared mutable state is obviously the enemy of thread safety here. So we have to go back to using separate bindings. So if you go back to using separate bindings to re-establish thread safety, what we get is that optimistic, instead of needing 15 to 20 milliseconds, now again we'll need 135 to 150 milliseconds to run, so it gets worse. But that's the price you pay for thread safety if otherwise you have mutable state. I am also a very big fan of immutability. If you've been at Richard's talk, then I hope that you will take this to heart. Actually, in Nashorn team, the compiler works on an abstract syntax tree of the parsed source code file, and we made that immutable. It was painful to make it immutable for the tree operations, but it totally paid off because we can parse and compile and transform the tree to the compiler pipeline up to a point, and then we can diverge there to say normal compilation and one-off continuation compilation. And we can rest assured that neither will step on the other's toes. So why I'm telling you this is you need to use separate bindings if your JavaScript program has mutable shared state. If it doesn't, you might as well use the same bindings. So my advice to you is keep it immutable, and if you can't, use a single engine instance, but use separate bindings. you can always use synchronization. We have a Java API with capital J. It has a bunch of useful methods. One of them takes a functional lock object and it just returns you a function that is synchronized on that. So, or if you are using Java libraries, just make sure they're properly synchronized. So the usual caveats of, yeah, you could do your manual synchronization and then live with the fact that sooner or later you'll have a deadlock, because people, even the smartest people, will produce deadlocking code. I know that I always did when I thought that I will not. So I will tell you a few things about. We only have 5 minutes, so I need to select what I want to tell you about. We had a lot of good questions. I don't mind, but we need to skip a few things. So one thing, so performance advice in your JavaScript code. Try to use homogeneous arrays. Nashorn internally specializes arrays. Every array, if possible, if it's uninitialized, starts out as an array of ints. And you fill it up with ints, and you have 1,000,000 ints, and you add a double. At that point, Nashorn will allocate a double array and will widen all elements, all those 1,000,000 elements, which is a linear cost, and then add your double into it. If you do an object, then it's even worse because it has to box every int that's there. But as long as you actually manage to keep your arrays homogeneous, Nashorn will, below, be very efficient about representation. The way we link array accessors and so on is also very efficient. It basically links pretty much straight through to native Java array element getter setter. So that's something that's very good. Probably needless to say, avoid eval. Eval is evil. Compiler will lose all of its reasoning abilities if you use eval, because eval can define new variables in a scope. It can change the values of variables. We need to presume that a function is variable arity if you use eval, because we don't know whether eval will reference the arguments object, right? So your code will become really slow if you use eval. With is just a slightly less evil. People love to use it because, oh, my code looks so nice. But here's a problem. It introduces, JavaScript otherwise has a nice lexical scoping, and the compiler can work with that. So if you reference a symbol, a variable, it can emit fairly efficient code finding out the lexical scope where it needs to be, or maybe it's in a local JVM, local variable slot. But if you use with, then this no longer applies. So if you have a variable x and then you access the identifier x from a with block, then we actually cannot store this variable x in a local variable anymore. It has to go into a scope object because it might need to participate in a dynamic scope lookup. Oh yeah, with actually creates dynamic scoping. So this is actually my my last piece of advice, and we have a question there. Okay, can you repeat the question?
So if you define, in JavaScript standard, you can define function inside of function.
Yep.
And inside of inner function, you can access auto-scope variable.
Yes.
In such case, such variables also will be put into the scope instead of maintained locally.
That's correct.
Is that correct? Okay.
Right. So if you have, we can consider this part of the question answers, right? So if you have a function f and you equals 1, and you have a function g, and you do something with it, then yep, this guy needs to go into a scope object, because then this all gets compiled to Java bytecode, and in Java bytecode you cannot pass lexical scope variables from one function to the other. So in that case, this guy gets shanghaied into a scope object in order to be able to pass to it, and this guy would not be. So yeah, but we are selective, so only those variables that are getting accessed will be passed into a scope object. With optimistic typing, that's not so bad, because the scope objects themselves are typed, and the accessors are also optimistically typed. So this return x, when it reads x, it will say, well, optimistically, maybe I can pull it out from the scope as int. And if it isn't, then we will actually recompile the inner function for a double or object or whatever accessor. So with optimistic typing, even this is pretty good because we store them in primitive fields in objects, and the accessors will also optimistically be emitted as primitives. So the question is, does it not get optimized away by JVM escape analysis? Might be. I don't know. To be honest, I don't know how good is current hotspot escape analysis, and on the other hand, I also don't care. I mean, in order to implement this feature correctly, this is the way to implement it. If the JVM is smart enough to manage to optimize this for me, yay. Otherwise, all right. Well. Thank you very much. I think we're out of time.